Teng.
From Alibaba. It's my honor to present our work here. The work is about how to build RPC using CXL shared memory. This is a joint work from Alibaba, Tsinghua, and Zhejiang University. CXL is a protocol not only for memory extension and disaggregation, but also for high-performance interconnect between machines. Unlike PCIe, CXL adds actual capabilities that let the CPU talk to the device. It defines three separate protocols. .io is for discovering and emulating CXL devices, including device register access, DMA, and interrupt support. .cache allows a processor to access a device, the internal cache and register, ensuring cache coherency. .mem enables the ability to access memory over CXL. These three protocols can interoperate to create three types of devices. For example, combine CXL with RDMA. RCMP enables internal access of CXL memory. With RCMP and RDMA cache coherency protocol, it can scale beyond rack. For Type 3, TPP introduced tied memory subsystem based on CXL memory and employs an operating system level machines for page replacement to enhance memory management. All these works are about how to improve the CXL. We would like to redesign the software with Type 3 CXL device as an underlying infrastructure of AI and key-value applications. RPC is our first goal. So CXL spec purpose to enable memory sharing. For instance, 2 terabytes pooled CXL memory system showcased at the FMS combines 8 Samsung CXL memory modulars with the XCON switch, enabling memory sharing among 8 computing hosts. This figure shows coherency memory sharing. With CXL.cache, CXL can be shared by all the hosts in the coherency domain if it defines mechanisms to enforce hardware cache coherency between copies of the same data. For instance, CPU 0, CPU 1, and CPU 2 can access the same memory region. The coherency model for each shared memory region is designed as either multi-host hardware coherency or software managed coherency. To support multi-host hardware coherency, it's required to check the host coherency state for each cache line. It also depends on tracking mechanisms such as Snoopy or full directory. In software managed coherency models, the coherency state of hosts is not maintained by hardware, but rather by host software through specific mechanism that establish ownership of cache line. When software takes the lead in managing coherency within certain memory regions, it can optionally use existing hardware coherency across multiple hosts for other regions to streamline ownership. SOTA RPC adopts message passing. The heavy network stacks of TCP RPC always cause high CPU overhead. Lots of research works explore RDMA to implement RPC to enhance performance. Those RDMA-based works can be divided into the raw RDMA RPC and pass by reference RPC. Hard and fast are designed for scalability with two-sided RDMA operations design. However, the actual data copies are invisible. RFP proposes pass-by-reference solution. For the RPC response, the server writes a reference to the client side. Then client uses the reference to fetch the response. So additional network round trips are needed to discover new incoming response under the memory passing paradigm. Using CXL-based shared memory instead of RDMA for RPC offers two significant advantages. First, the traditional architecture requires clients to communicate over the network, which will become a bottleneck. In contrast, CXL memory avoids involving the network. Second, CXL provides better addressable access, enabling the link pointer and allowing for in-place update. This eliminates the need for serialization. So when design CXL-based RPC, it's essential to consider the architecture from the perspective of shared memory abstraction. So our platform is based on HydraRPC FPGA and HCT platforms with SPR CPU. The server has 96 hyperthreads, and the CXL FPGA is inserted into the PCIe slot of one node and connected to the other node with MCIO. We use the CXL 1.1 driver as the current hardware. We initialize the CXL memory in the DEX model with DEX control tool. There are several constraints in our platforms. First, it's impossible to use shared memory as general purpose system RAM through each CXL link, as it will lead to corruption of each other's data. Thus, RPC should manage reservation of the memory to prevent uncontrolled access. Second, to ensure that data are read from CXL instead of the local cache. Cache invalidation are required. Finally, to ensure that data are written to CXL instead of only local cache. Flashing of cache line needs to happen after write. So we designed HydraRPC, which is a CXL-based RPC. It uses CXL to avoid the expensive network around and memory copies and serialization. Multiple clients and servers connect to the same CXL memory via physical link or CXL switch. So for each RPC connect, there are two message queues and the corresponding data area in CXL memory. Message queues are responsible for passing the reference as the request or response buffer, and the data area stores the raw data of the request and the response. Each entry in the message queue is 64 bits in size, contains an embedded offset to the data area and a 1-bit arrival flag to allocate memory for the request or response. We employ a user space level memory allocator. This allocator manages the CXL memory by mapping the device memory region. HydraRPC maintains at least an RPC service in each physical server. When the application is deployed, it connects with such a service, and the service will distribute the global address of message queues and the data area in CXL memory for both server and client side. Then following a typical handshaking protocol between server and client, the RPC connection is established. So then HydraRPC in its data path, there are 3 steps. For request phase, the client writes the user-defined request data to the pre-allocated memory in the data area, which is cache line aligned to enable non-cacheable sharing. Next, the client appends an entry to the request message queue before sending the net request. There is no need to wait for the response from server side. Meanwhile, the server puts the arrival flag in the tail entry of the request message queue. For execution phase, once gain the new request, the working process uses the offset in the entry to execute the request. For lightweight RPC requests, HydraRPC follows the run to complete principle to inline the execution phase into the pooling process. If the server has prepared the response data, it writes it to the pre-allocated memory in the data area. To reduce memory copy, the server can use pre-allocated memory directly during execution. For response phase, the response phase may include data to the client side, such as the server appends an entry to the response message queue. Then the entry in response message queue is pulled by client who sends the request. The RPC process is considered complete when the client acknowledges the response. So without a stored cache, memory sharing is not visible to any user. A single cache coherent domain for multiple servers will be available in the upcoming CXL version 3. Thus, applications should ensure that shared memory is used properly. We provide two alternative mechanisms to enable non-cacheable sharing via bypassing CPU cache. The first is MTRR. It provides a way to control access and cacheability of physical memory regions with certain ranges of memory addresses. It allows for write-through, write combining, and write-back caching. We gain the physical memory region of CXL memory from SART in ACPI, and then use I/O control to set the attribute of such memory region as uncacheable. Intel provides specific instructions such as CL-flash, CL-WB, or NT-store to flash or directly write data to CXL. To ensure that data are accessed from CXL memory instead of local cache, we use CL-flash and prefetch to bypass the local cache. Then is followed by a memory fence to synchronize non-temporal access. These two bypassing caching mechanisms show the same performance, thus we don't distinguish them in evaluations. HydraRPC requires a notification mechanism to inform the client about arrival of request, so it use pulling on the CXL memory to detect incoming request or response. In this approach, the CPU reads the arrival flags of entries and initialize processing when the arrival flag is valid. To mitigate the issue of spanning on a memory location during busy pooling, we use these two SSE3 instructions, mmonitor and mwait. We can issue a monitor instruction at the cache line granularity for the circular buffer. Subsequently, mwait instruction is executed to help the CPU and conserve power. This CPU is then awakened when the data is modified. It reduces CPU footprint and improves the performance of memory pooling. Also, we have a plan to support interrupt-based notification. In our implementations, the allocation of the message queue and the data area follows the separate paths. For the message queue, we use a fixed size memory pool, and the ownership of the message queue is up here. For the data area, we use a two-tier allocator to alleviate the overhead of selectable allocation. When a physical machine has multiple connections with another physical machine, those connections can share a single message queue. Then the pooling process can follow the same way. It reduces the memory footprint and mitigates the heavy CPU utilization. Besides, HydraRPC employs the sliding window protocol to control the data transmission flow. The sliding window limits the number of messages that can be sent before an acknowledgement is received. This window size can be dynamically adjusted based on the conditions of CPU utilization or receiver processing capabilities. When the client needs to push multiple requests to the request message queue, it can control the number of additional requests that can be sent. Upon sending a request, the client starts a timeout timer. If the corresponding response is received before the timeout, the RPC task is completed, and the client moves the window to send the subsequent task. However, if a timeout occurs, the request must be resent. Sliding window can prevent access congestion of the CXL, ensuring a consistent data transmission rate with high reliability for applications. Finally, is our evaluation. The upper table shows the latency comparisons between HydraRPC and our 4 baselines. HydraRPC achieves an average latency of 1.47 milliseconds compared to 4 times CXL access. MRPC has little actual latency. Compared with MRPC, HydraRPC speeds up the average latency by 5 times and the %99 tail latency by 4 times. As shown in the left figure, HydraRPC speeds up RPC and RDMA RPC by 100 times level when the size is from 64 bits to 2 megabits. The cause of performance degradation of RDMA RPC is that they are bounded in the maximum bandwidth of network. In HydraRPC, the data can be updated in place, and it can further exploit the high bandwidth of CXL. We also evaluate HydraRPC with different sliding window size from 0 to 16. The throughput of HydraRPC can achieve 1.28 MOPS when sliding window size is 16 and is 2 times higher than HydraRPC without applying sliding window. Last, we evaluate the scalability. The performance of HydraRPC is higher than MRPC and RDMA RPC. RDMA RPC performs degradation when RPC connection number is higher than 48. In contrast, the throughput of HydraRPC increases from 28 to 49 MOPS when the connection number is from 48 to 96. This is my presentation. Thank you. Any questions?